In the last lecture, we had introduced first order logic, which is also known as predicate logic, to express the different domain specific knowledge that we require in order to build an intelligent system. In today's lecture, we will be talking about different ways and means which are used for reasoning using such a language, that is the first order logic. How we can use the different sentences of first order logic to reason about about a particular problem. That is what we will start looking at from today. Before we go into the inferencing process proper, we would like to first show or rather revisit some of the notions that we had presented in the last lecture. So, to start with, we had introduced sentences in first order logic. What are sentences? A predicate is a sentence. And what is a predicate? That we had already seen. And if SEN, say a short form of any sentence, if SEN and say SEN prime, this is SEN prime, that is a negation of SEN. Suppose there is a sentence or the negation of a sentence. These are sentences. If these are sentences and x is a variable, then SEN is a sentence, not of SEN is a sentence. There exists x such that the sentence is true is a sentence in first order logic. For all x, SEN is a sentence. SEN and now these two are equivalent. If you look, I have sometimes written as the not symbol as this and sometimes as this prime, but essentially these two are meaning the same thing. So, sentence and the negation of the sentence is a sentence. Sentence or the negation of the sentence is also a sentence. Some sentence suppose we are considering two sentences. Please excuse me, this is not the proper way. Say SEN and SEN prime are two sentences. Suppose there are two sentences, okay, and not SEN is the complement of sentence. What I said just now was not right. So, let us see. If SEN is a sentence and SEN prime is another sentence and x is a variable, then SEN is a sentence, not of SEN is a sentence. There exists x, SEN is a sentence. For all x, SEN is a sentence. Sentence sen and sen prime, the conjunction of these two sentences is a sentence. Sen or sen prime, that is a disjunction of these two sentences, is a sentence. Sen implies sen prime, that is one sentence is implying the other, is also a sentence. And in proper predicate logic, nothing else is considered as a sentence. So, what we really mean is we start with the predicate, say P x, okay, tall x, okay, that is a sentence, and say strong y is another sentence. So, tall x, so tall x is a predicate and hence it is a sentence. Okay. There exists some x such that tall x is a sentence. For all x, tall x may not be true, that is for all people they are tall. For all x, tall x is a sentence, may not be true, okay, may not be satisfied in a particular domain. Tall x and strong x or strong y is a sentence. Tall x or strong y is a sentence. Tall x implies strong y is another sentence. So, these are sentences. That means, if we take a predicate and the negation of that predicate is a sentence, since the predicate itself is a sentence, existential quantifier, which we had introduced in the last lecture, existentially quantified sentence is a sentence, universally quantified sentence is a sentence, the conjunction of two sentences are sentence, the disjunction of two sentences is a sentence, implication, one sentence implying the other, is also a sentence, and nothing else is a sentence. Now, let us look at some example sentences. Say, if we write the predicate birthday x y. So, this is a binary predicate, right. Why is it a binary predicate? Because it has got two variables as parameters. What is the meaning of this in a particular domain? It means that x celebrates birthday on the date y. So, Tom celebrates birthday on 1st January, or Julie celebrates birthday on 1st March, etc. So, in general, I can say x celebrates birthday on date y can be written as this predicate. So, this is a sentence, right. Now, if we write for all y there exists x such that birthday x y, what does it mean? Let us first try to understand. Looking at this predicate, we can see x celebrates birthday on the date y. And what does this sentence mean? This is a sentence according to our last definition. This is also a sentence because it is existentially quantified. Now, you can say that well, you had said there exists x sen is a sentence, but again you are saying for all y. So, let us go back a little bit and let us have a look at that again. You see, here it is said that an existentially quantified sentence is a sentence. So, this whole thing is a sentence, and therefore, if I apply a universal quantifier over a sentence, then that also remains a sentence. Okay. So, here we can see that x celebrates birthday on date y, and what does it mean? That is for all y, that means for all dates, all possible dates, there exists some person who has got a birthday on that date. Now, if I express this in English, then it would mean that for all dates there exists a person who celebrates his or her birthday on that date. Okay. That is, every day someone celebrates his or her birthday. Now, this complicated, relatively complicated notion can be very succinctly, in a very expressive manner, in a very brief and packed manner, we can express in the language of first order predicate logic, as is shown here. Okay. So, this is a sentence, and when I quantify this with an existential quantifier, that is a sentence, and this whole sentence when quantified with an universal quantifier is also a sentence. So, next let us go to another example. Say, when I write brother x y, that means that x is the brother of y. Okay. Now, when I write loves x y, that means x loves y. These two are predicates, both binary predicates, and these two are also sentences. Now, if I write, now I want to make a more expressive statement. Brother x y implies loves x y, and that is universally quantified over all x and all y. That means, for all x and for all y, if x is the brother of y, then x will love y. Whether in real world that is true or not, that is a different issue, but this is a valid sentence in terms of this is a proper proper sentence in terms of the language of first order predicate logic. So, what is the meaning of this? The meaning of this sentence is everyone loves all of his brothers or her brothers, all right. Now, this is a valid this is a correct sentence. Now, you might have noted that often when I am saying valid and then I am just changing that word valid, because I am using this word as a valid sentence in normal English, but in terms of logic, since we have already discussed the interpretation of a sentence in a particular domain, this word valid has got a special meaning. When a sentence is evaluated to be true in a particular domain, then the sentence is said to be satisfied. But when we say a sentence is valid strictly in terms of first order logic, then actually you mean that for all possible domains, this sentence will evaluate to be true. So, that is special logical, it has got a special logical connotation. Although in our normal day to day English, we often use the word valid in a much looser sense, and that is why whenever since I am talking about logic and normally the word valid is coming to me, but I am trying to retract from it. So, it is a correct sentence in terms of the grammar of first order logic. So, everyone loves all of his or her brothers, that is expressed in this sentence. Now, let m x represent mother of x. Then I want to express this sentence, English sentence, everyone loves his or her mother. How would I express it? You can think yourself. Let suppose by mx I denote, m is this is a predicate, this predicate will denote mother of x, and I want to express everyone loves his or her mother. What would be a correct first order predicate logic sentence in order to express this? It would be for all x loves x mx. Why is it for all x? Everyone. So, I can take any x and whatever x, Tom, Dick, Harry, Ram, Sham, whatever you select, Jagjit. Now, whatever you select x, then x will love mother x, mother of x, because mx denotes this. So, these are some examples of first order predicate logic sentences. Now, till now we are giving examples from our day to day usage, but when we come to a little more mathematical domain, then also we will find that first order logic can express a lot many things in a very powerful and succinct manner. Here is an example. Suppose any number is the successor of its predecessor. Any number is the successor of its predecessor. I take any number 7. Okay. What is the predecessor of 7? 6. And what is the successor of 6? 7. So, this is a very true sentence that any number is the successor of its predecessor. So, in order to express this, I choose two predicates, successor x and predecessor x, suc x, pred x. Now, with these two, and I also introduce another predicate equal x y, all right, which means x and y are equal. Now, using these three predicates, I would like to express this English sentence, any number is the successor of its predecessor. How can I do it? For all x equal x successor predecessor x. Now, let us try to see what it means. for any number, if x be the number, then predecessor of x will return me the predecessor of that number, and the successor of that number will return me the successor of predecessor x, and this number and this number and this number should be equal. Say x is 20, then predecessor x will return me 19, then I am computing successor of 19. What is that? 20. So, 20 is my y and the x was 20. So, these two are equal. You see, the same thing can be expressed in this way. Now, you can take it is for all x. So, you can take any number and this will hold true. Okay. Now, you can think that well, I could have represented it that in a better manner. Why do not I use the equality sign? Say I try an alternative way of representing it. So, the previous example can be represented very succinctly as for all x, successor of predecessor x is equals x. Now, you can, if you are careful, you can note that I have put in this equality in a different color. Unfortunately, the definition that of sentences and the valid operators that we had mentioned in the case of first order logic did not have any equality operator. They were predicates, they were quantifiers, but this equality operator was not there. Therefore, we had to take recourse to this sort of predicate equal x y, which was essentially denoting x equals y. In the standard predicate logic as defined, this equality operator does not exist. Therefore, this is not a valid, or again sorry, it is not a correct, grammatically correct predicate sentence. However, it was found that this limitation was really becoming a little difficult to maintain, because often if we had the equality operator allowed in predicate logic, we could have expressed many sentences in a better way. Therefore, first order logic was extended with first order logic with equality. It was extended to first order logic with equality. In first order logic with equality, we are allowed to use the equality sign between two functions. This is for representational ease, and so we can now modify the definition of sentences that we had provided, where we had written SEN prime as two sentences. We can call them as terms. Okay? Each of these SEN, there are different ways of defining this. We had said SEN prime are sentences. Therefore, for all x, SEN is a sentence. Now, whenever it becomes a sentence, we can call that small sentence as a term. So, now we extend this definition as term equals term is also a valid sentence. Okay. So, we can now use this equality operator as a part of the first order predicate logic repertoire or the valid operators dictionary. Now, in the last quiz that was given to you, now with this revision of predicate logic, now let us work that out a little bit. The first sentence that we wanted to represent in predicate logic was some dogs bark. Some dogs bark. You must have tried this, and this one we can represent as a first order predicate sentence as there exists x because it is sum such that dog x and bark x, because there are why do I need this existential operator? Because some dogs bark. I did not say that all dogs bark, but if all dogs bark, then also this will be true, right, because in order to prove its truth, I just need to find one dog, one x which is a dog and which barks, then this sentence is true. The next example that was there is all dogs have 4 legs. All dogs have 4 legs. Now, this can be represented as for all x, dog x implies have 4 legs x. I am sorry, here I should have put another parenthesis. Please, here there should be another bracket, because this for all x, the scope of this for all x is over this entire sentence. So, there should be a corresponding matching parenthesis with this parenthesis, all right. So, I have missed that. So, actually there should be another parenthesis here. You may correct it in your notes. So, for all x, dog x implies have 4 legs x. Now, there could be another alternative representation to this. Say I could have said here in the first one I have used this, both these are unary predicates, because have 4 legs is a predicate which is having only one operator, one variable parameter, whereas here for all x, dog x implies legs x 4. So, legs is a binary predicate which has got one is the variable x and here is a constant term. So, for all x, here again I have missed one parenthesis, all right. For all x, dog x implies legs x equal to 4, sorry x 4. So, this is another way we can do. Now, just a question here, those of you who have noted it carefully, could I write this as for all x, dog x and have 4 legs x? Would it be correct, or is this a better representation? Just think about it. I hope you understand what I said. I said that here I have said for all x, dog x implies have 4 legs x. If I had written it as for all x, dog x and have 4 legs x, would there be any problem? That is another issue. In this case, probably, okay, I leave it to you to think. Now, another example that was given in the last quiz was all barking dogs are irritating. All barking dogs are irritating. Now with this discussion that we had, revision of first order logic, I will leave it to you, do it yourself, all right. I will not give the answer here, I am sure you will be able to do this. Okay. The next problem was, sentence that was asked to be converted was, no dogs purr. One possible representation of that is, there does not exist an x such that dog x and purr x. There does not exist an x such that dog x and purr x. Now, this is one way of representing it. Could there be another alternative way? Just think, if I had started this as for all x, suppose for all x, then how would I have written this? For all x, dog x implies what? Implies not purr x, or could I write it for all x, dog x and not purr x? all right. It is also possible this, I hope you remember the duality thing that we had discussed in the last lecture, that any existential quantification can also be converted to universal quantification. So, you try that in that way, but no dog's park can be represented in this way. Now, here was the next example. Fathers are male parents with children. Fathers are male parents with children. Now, this is a solution to that. For all x, if x is a father, that implies that x is a male and x has children. So, I can represent this as father x implies male x and has children x. Okay. Now, the next example that was there, students are people who are enrolled in courses. Students are people who are enrolled in courses. Now, you should be able to do that now. Say try something like this, student x implies people x, etcetera, etcetera, in that way, and put in the proper quantifier to that. And so, this is again, although it was given in the last lecture, and many of you, I am sure you have done it, and if somebody has done it wrongly, now with these given examples that we have discussed, please try it again and do it yourself. All right, this is a simple one you will be able to do. And I would suggest that if you take up any AI textbook, there are a number of examples that are there, or even without an AI textbook, you can take very normal sentences that we use in our day to day life and just take it as a game, whether you can write down them in the first order logic. Also try another thing, whether you can represent some of these in the form of propositional logic, and when you cannot, think why you cannot do it in propositional logic and try to do it in predicate logic. And maybe there will be some sentences which you cannot really capture in predicate logic also, but those are different cases, but you will find many sentences that we use in our day to day conversation, simple sentences that you can represent in predicate logic. Next, we come to, so this is all about the revision that we intended to do about the first order logic. The next thing that we will be doing is inference rules, because we want to, given these sentences which are presented in first order logic, our ultimate objective is to reason using them. And in the inference rules, there are some basic techniques which we must learn. One is universal elimination. That means, if we have a sentence like this, for all x likes x flower, then likes x flower will hold for all x. Therefore, I can substitute this x by some constant, like say a particular name Shirin. Shirin likes flower. There will be nothing wrong that I am doing, because you have said for all x. So, whenever there is an universal quantifier, I can drop it and represent this with a constant term. So, eliminate this for all x part, and the substitution of that x in this part of the parameter should be done with a constant term. That is technique 1, that is universal elimination, that is elimination of universal quantifiers. The next thing is, which is a little more complex, is existential quantification, elimination of the existential quantifiers. Now, why are we doing this? We are trying to come to a stage where we can take these predicate sentences, these predicate logic sentences, and use them in our reasoning in a mechanical way. That is the purpose. So, we are trying to give them a different form using which where we are removing the universal quantifier, but what will happen in the case of existential quantifier? For universal quantifiers it was so simple, for all x p x. So, I can always drop that x and put in any constant because it will hold for all x. But what happens in the case of existential quantifier? There exists some x for which p x is true. Now, which x? With which x can I replace that x part of p x? So, that is, this method is also known as skolemization, all right. Say here, for all x likes x flower, sorry, there exists x such that likes x flower. Now, this one means that likes person flower. Now, this person is some person, some particular person which is not there in the knowledge base, and if I can find out that person, I can put that in, all right, and that particular person, all right. Say there is a sentence, there exists x such that likes John x and food x, say x is a food, and there exists x such that John likes x. Now, then there is some x which John likes. Suppose I find out apple, then I can represent that particular x parameter with apple and remove that existential quantifier. This method of finding out a particular constant that satisfies the predicate there exists x such that John likes x, that finding out that particular constant that satisfies this is known as skolemization, and when we can find that out, we can replace it. Thus, we can, by eliminating this existential quantifier, we can get such a sentence where the existential quantifier is not there. Just the opposite, in some cases we may like to introduce existential quantifier, that is existential introduction. Suppose I am given a sentence likes Shahid flower. Now, I know that Shahid likes flower, then I can certainly write it, it can be written as there exists x such that likes x flower, because I know that it will always be true, because I can replace this x with Shahid and there will be no problem. So, this is, please note that this is just the opposite of existential elimination and this existential introduction, all right. Now, with this, let us go into the reasoning and start with a particular problem, and the problem is defined over here. Look at the problem, where we are making a statement which may appear, I am going slow. So, it may appear to be a little complicated to you at the beginning. If a perfect square, what is a perfect square? 16, 25, all those things are perfect squares. If a perfect square is divisible by a prime p, by a prime number p, say 25 is a perfect square and is divisible by a prime p 5, all right, then it is also divisible by the square of p. This is one sentence I state, okay, in mathematics that is right, all right. The next statement that I make is every perfect square is divisible by some prime. Every perfect square is divisible by some prime number. take a perfect square 16, it is divisible by 2, it is a prime number, all right. I also say 36 is a perfect square. So, what are the three statements that have been made? If a number is a perfect square, then it is divisible by a prime number, and if a perfect square is divisible by a prime number, then it is also divisible by the square of that prime number. And every perfect square, now these are important, every perfect square is divisible by some prime. 36 is a perfect square. Now, with these three statements, now I want to reason to find out, does there exist a prime q, a prime, any prime number, a particular prime number q, such that the square of q divides 36? Okay. That is what we want to find out. Please note this down, because the next step where I will be going is to convert these into predicate sentences. I hope you have noted down this problem. The next thing that we will be doing is convert them into their predicate form, in the first order predicate logic form. So, here is a sentence. If a perfect square, I take the sentences one by one. Now, this is the method. You have to take the sentences one by one and convert them into predicate form. So, if a perfect square is divisible by a prime p, then it is also divisible by the square of p. That was the statement made. So, I write it as for all x and y. You can write it as for all x, for all y also. This means the same thing. I should have put a bracket for all x and for all y, perfect square x, if x is a perfect square, and prime y. So, y is a prime, and divides x y, that is this prime y divides x, that takes care of this if a perfect square is divisible by a prime p. Note that although over here I have said p, in my sentence I need not write p, I can write x, y, anything, but I must be consistent in this sentence. Then it is also divisible by the square of p. So, this implies divides x, which is a perfect square, by the square of y. Now, y by the square of p. Now, I did not use p in my logic sentence, I have used y. So, I have used y as here also, all right. So, if a perfect square is divisible by a prime p, then it is also divisible by the square of p. So, this is the conversion of this sentence into the predicate form. Next, every perfect square is divisible by some prime. Every perfect square is divisible by some prime. Now, since that is there was every perfect square. So, for all x, perfect square x, there is some prime number which divides it, right. There is some prime number which divides it. So, I put in for all y, for all x there exists y, some prime is there such that y is a prime. So, perfect square x and prime y and divides x y, divides x is divided by y, all right. So, please note carefully that x has been universally quantified. Why? Because this I am talking for every perfect square, and y has been quantified with existential quantifier. Why? Because I have just said that there is some prime which divides it, not that all prime numbers will divide it. So, there exists y, which is y is a prime number as stated here, and divides x y, all right. So, these are two sentences. What was the next sentence? 36 is a perfect square. That is a very simple one. 36 is a perfect square. So, I can write down perfect square 36. No problem with this. Now, does there exist a prime? That was my objective. That was the thing that I wanted to prove. Does there exist a prime q? some prime number q such that the square of q divides 36. So, that query I write down as, I assume. So, now in order to answer this question, does there exist, I can also pose it as a theorem which I will be proving. If I can prove it, I can say, I just make a statement, there exists a prime q such that the square of q divides 36. I make that statement and then I try to prove it by inference. If I can prove it, then there exists an x, and if I cannot prove it, then it does not exist. So, this particular query that is shown here, this query can be converted in the form of a predicate, which I shall try to prove using my reasoning mechanism of first order logic. Now, therefore, I can write it down as there exists y such that y is a prime and divides 36. I can divide 36 by the square of y. So, these are my sentences, all right. Next, so with these I have got a knowledge base, and what is that knowledge base? These statements for all x y, perfect square x and prime y, all right, and divides x y implies divides x square y, that was the first sentence. The second sentence was this, the third sentence was this that we have just now done. Now comes the reasoning, the inferencing from 2 and universal elimination. What was 2? 2 was, let us see again, 2 was this, for all x, perfect square x and prime y and divides x y. Now, when I eliminate this, I want to prove it. I am dealing with a particular perfect square, that is 36, that is of interest to me, and perfect square 36 I know. Therefore, I can put 36 in place of x and remove this for all x part. That was, I put 36 here as well as I put 36 here. That was our inference method of elimination of universal quantifier, right. So, I eliminate that, then I get a new clause, for all x part is gone. So, there exists y perfect square 36 and prime y and divides 36 y, that is just the thing that was here, and from here I have replaced these two x's with 36 and have removed this universal quantifier and have got the fourth clause. Now, from this 4 I want to eliminate this existential quantifier, all right. Now, existential quantifier elimination is by Skolemization, that means I will find out some constant which is a prime. So, let me put some constant p, all right, and remove this existential quantifier and get this new fifth clause, perfect square 36 and prime p and divides 36, p divides 36. Now, from 1 and 5 with this 5, this is the fifth one, this is the fifth one, and what was the one? One was this. I have eliminated from 2, but say here for all x y, perfect square x and prime y and divides x y implies divides x square y. Now, 1 and 5, what is my 5? This one I can get. So, I get perfect square 36, prime p divides 36 p. Perfect square 36, now this was a universal quantifier. So, I put 36 here and in place of y I put p and I can remove these two straight away, all this quantification I can remove. So, I get perfect square 36 and prime p and divides p 36, that was this part, that was clause 5, implies divides 36 square of p, all right. So, that is the sixth one that I am getting, all right. Now, this is the sixth one. What is the next one? So, I get divides 36 square p. Now, from 5 and 6, prime p and divides 36 by square of p. What was 5 and what is 6? 5 was this perfect square 36 prime p and divides 36 p, and I get p as divides 36 square of p. So, in place of p I can simply put square p, here also square p. So, what do I get? Perfect square 36 and prime square p, all right, prime p and divides 36 square p. Now, I can now you see the use of existential introduction. I introduce this existential quantifier, and therefore, now all these are constants. I put in place of p I put a variable y, here also for p I put a variable y, and introduce this existential quantifier, and I get there exists y such that prime y and divides 36 square y. Now, if you recall, that was my thing to be proven. Let us go back to that and let us see. My objective was to prove this. Does there exist a prime q such that the square of q divides 36? That was this thing, prime y divides 36 square of y. That is the thing I wanted to prove, and through the technique of universal elimination, existential elimination, and again existential introduction and replacement of variables, I get this same thing. That means, I could prove this, I could infer this, all right. However, inferencing would have been easier if the knowledge base consisted of the following sentences. Say, you have noted down the problem, so you can try it in different ways, okay, and I would encourage you to do that. Suppose the knowledge base consisted of the sentences like this: perfect square 36, which was there, prime p divides 36 p, and for all x y prime perfect square x and prime y divides x y, then probably the inferencing would have been easier. Now, I would like to introduce a very important notion that is called a particular type of sentences, which is known as horn sentences or horn clauses. These horn sentences are also known as horn clauses, and this has got a tremendous application in the case of inferencing in predicate calculus. Now, what are horn clauses? Now, let us look at this slide. The horn sentences are, what are the possible horn sentences? Any atomic sentence is a horn sentence. Any atomic sentence is a horn sentence. So, a sentence like perfect square 36 is a horn sentence. Implications with a conjunction of atomic sentences, where atomic sentences are joined together, conjuncted, and a single atom is on the right. So, a sentence like this: for all x y, perfect square x and prime y and divides x y implies divides x square y. That is a horn sentence. So, and there is no existential quantifier. There should not be any existential quantifier. Now, a couple of things you can just note, that on the left hand side of this implication, there are atomic sentences, there can be negations on that side, all right, also, and on the right hand side we have got a single atom, and there are no existential quantifiers. So, if this be our horn sentence, you see that means this, that if I had this side is a conjunction, there is no ORing, and here also there is only one unit. Now, if a particular sentence given to you is not a horn sentence, then we will have to convert it to the horn sentence. How can I convert it to a horn sentence? We know that existential quantifiers can be removed using existential elimination. We can eliminate the existential quantifiers by the process of skolemization. If the existential quantifier is outside any universal quantifier, a Skolem constant is introduced. You know a Skolem constant? A Skolem constant is a particular constant that I find out from the knowledge base and replace it in place of that particular variable y, for example, which was quantified with that there exists, right. So, if I have something like this, there exists y, prime y implies prime p, there exists y, prime y. Now, y being existentially quantified, I can put a Skolem constant p in place of this. So, I can get this is a horn sentence. Otherwise, a Skolem function is introduced. When I do not find a constant, I can still leave the responsibility, as if I am leaving a responsibility to a function, that well, that function is a magic function which will somehow find out a particular constant value which will satisfy the clause or the sentence. It will find out if there exists something that the Skolem function will find out that constant. For example, here for all x there exists y, prime y and divides x y. This one can be here y is universally quantified. So, I replace this there exists y with for all x prime, say p d is a function, all right, say prime detector or whatever you can think of, x on x that divides x. So, given x I find out some prime p d and divides x p d x, where p d x is a Skolem function. This is a Skolem function. So, using that I can get rid of the universal quantifiers, and the and part can always be eliminated on the other side. If there be and part is there, the conjunction is there on the right hand side, I can always do say prime p and divides x p can always be written as two clauses like prime p and divides x p. It is possible. I can break them up into two different clauses and each of them remain a horn clause, because any atomic sentence is a horn clause. The other thing that is often required in inferencing in first order logic is substitution. Substitution replaces variables with constants. Variables are represented with constants. How? Say I am using substitution is an operator, x is replaced with 49. Then if I do this substitution, then perfect square x will become perfect square 49. Okay. Substitution of x with 49, look at this notation, x is substituted with 49 and y is substituted with 7, then divides x y with this particular substitution, it will reduce to x 49 replaces x. So, divides 49 and y is 7. So, 7 divides 49. This is a substitution operator where I have to define a consistent substitution, and then from this divides x y I can come to this. Okay. Now, this gives us a very nice operator which is often used in predicate logic, that is unification. I shall not go into the details of unification, but will try to give you the flavor of unification through examples. There are algorithms given in any artificial intelligence book where you can find that the unification algorithm, but just try to understand that unification is the process of finding a particular substitution that will make two atomic sentences identical. when two atomic sentences are identical, then I can use one for the other, and that is our attempt, that is often our attempt that helps out in inferencing, which we will see in the next lecture also. But here let us look at, so what is a substitution? All substitutions cannot unify. For example, I unify, say there are prime x, prime 7 and prime x. Now, I apply the substitution x substituted by 7, then I can, this substitution really makes these two same, identical. So, they can be unified. So, this means it is possible to unify prime 7 with prime x with the substitution of x with 7. It is possible, please look carefully, it is possible to unify these two sentences, divides 49 by x, x divides 49 and divides 7y. These two can be made identical with the substitution of y by 49 and x by 7. So, if I do this, then what will happen? This will become x by 7. So, divides 49 7 and divides y by 49, divides 49 7. So, this particular substitution is possible which unifies these two sentences. On the other hand, you see unify prime 7 and prime 17. It is not possible, because there cannot be any substitution that will make this change these to constants. On the other hand, here you see unify, the attempt to unify divides 49 x and divides x 7. It is not possible, because if I substitute x, I can substitute x here with a particular variable. In that case, I will have to again replace it here. These two cannot be unified, these are not possible. So, it is not the case that always I can find a substitution, but if I can get a substitution, then it will be possible to make two clauses identical, and that will help us in inferencing, which we will show in the next lecture. So, in today's lecture we conclude at this point. We had, what have we done? Let us quickly revisit. We have had a revision of first order logic, how to make the sentences, and we have seen the basic steps of universal elimination, existential quantification elimination, existential quantification introduction and substitution, as well as we have seen horn clauses, and horn clauses, how non-horn clauses can be converted to horn clauses, that we have also seen. So, with this background, we will move to the next lecture, which will be further reasoning techniques on first order logic. Thank you.